Welcome all. Today we are going to discuss about a different topic called group automorphism. So we all have heard of groups and group theory. Some of you in high school might not have been exposed to group theory. It is a very simple idea. Suppose you have a set S and a binary operator G on S, which is a function from S cross S to S. Like you take a pair of elements of S and map it to another element of S. Then the group along with this binary operation G is called as a group under the following conditions. First one, it must have an identity. An element is called identity if that when operated with any other element of the set gives you the same element of that set. That is, we call E as identity if E star any element S equal the same element S, which is also S star E. The star here denotes the group operation. Then that element E is called as identity element. Second one, inverse must exist for every element of the set S. What is the meaning of inverse? We call an element K inverse of S if K star S equal the identity element. So first you have to identify the identity element. Later you have to prove the existence of inverse of every element S in capital S, such that K when operated with S gives you the identity, which is also S star K. So here we call K as the inverse of small s. So both these conditions must be true for all S in capital S. Third condition and one of the most important condition is the associativity property. This might be very much familiar with you. You have to check whether the group operation satisfies this or not. That is S1 star S2 star S3 equal S1 star S2 starred with S3. Again, the star is the group operation or the binary operation which we started off with. If it satisfies, if the pair S comma G satisfies these three conditions, then S is called as a group under the group operation G. Then we call S as a group. An example will make it more clear. Integers, the set of all integers Z with addition as the group operation will make it a group because identity element is 0 and inverse of a particular element A is just minus A, which is also an integer, and addition is associative. These three properties make it a group. The idea behind definition of this is the way we deal with abstract things, and group is a way of organizing or a particular set that is very nice to work on. You can have some non-trivial examples for group, but I'm skipping it for now. We will look into group isomorphism now. Automorphism is a type of isomorphism. It is simple. We consider a group G and we call a map H from G to another group K, an isomorphism if H is bijective and it respects the group operation. That is, H of G1 star G2 equal H of G1 dot H of G2, where star denotes the binary operation associated with group G, whereas dot denotes the binary operation associated with group K. So it respects that, and H is bijective, implies that the map H is a group isomorphism, which maps elements of group G to elements of group K. K is our target group. If H being bijective is removed, then the resultant map is called as group homomorphism. We will consider a special case of group homomorphism where the function is bijective, and that's when it is called as group isomorphism. Well, a group automorphism is just an isomorphism from the group to itself. we call the function h a group automorphism if it's an isomorphism from the group to itself. So that means it is bijective and respects the group operation. Let us consider an example of group automorphism. Suppose h of x equal minus x, where h goes from the real numbers with addition operation to real numbers with addition operation, the same group. Let's prove that it's bijective. Since you have minus x relation, the entire real number is covered by appropriately choosing the negative of the original number. And it is also injective because if you assume h of x1 equal h of x2, that imply minus x1 equal minus x2, which imply x1 equal to x2. This means it is both injective and surjective, implying that it's bijective. Let's check whether it satisfies the group operation or not. It has to respect the group operation. So let's consider h of x1 plus x2 being equal to h of x1 plus h of x2. I know h of x1 plus x2 is minus of x1 plus x2, whereas h of x1 is minus x1 and x2 is minus x2. So clearly both of them are equal, and therefore this is a group automorphism. And now the question we are interested in is as follows. Now it turns out that set of automorphisms of a group forms another group called as automorphism of the group, or G, represented by or G, where G is the original group. The group operation is function composition. Underlying group operation is the function composition. That is, you compose two different automorphisms and you get another automorphism. Think about it. If there exists one automorphism, then its inverse is actually another automorphism, and that will be the group inverse element of the original one. An identity map is the identity element of this automorphism group. Alright, now let's get started with our actual question. The question is, if G is a cyclic group, then is automorphism of G cyclic? So if it is cyclic, you have to prove, and if automorphism group of G is not cyclic, you have to give a counter example. But how to come up with that? So let's see what is the underlying concept. A cyclic group is simple. The cyclic group is generated by exactly one element. You have A as a generator, let's say, then A square, A cube up to some A power n minus 1, and A power n will equal the identity and it repeats. So this is entirely generated by the element A, and this is called a cyclic group of order n. Now, if you want to define the automorphism group of that, it will just be set of automorphisms, so set of functions in fact. E is the identity map, and you have some other maps like F1, F2 and so on. Is it true that this group is also cyclic if group G is as displayed? Now think about this question for a few moments before looking into our solution. To get started, we are interested in functions that are bijective, that maps group G to the group G like this. Let's call the automorphism as F, and you have the identity A square, A cube, so on up to A power n minus 1. And in the codomain, you have the same enumeration E, A square, A cube and so on till A power n minus 1. So the pivotal argument here is that if you are able to map the element A to some element of the codomain, then you are done with mapping all the other elements by the group operation which takes A to A square, A cube and so on. Let me elaborate on that. First of all, identity must map to identity. This is crucial in order to respect the group operation. Let's say A maps to A square, that is f of A equal A square. then you see f of a square is nothing but f of a times f of a, which is a square times a square, that is a power 2 square. Next, f of a cubed, this is going to be f of a square times f of a, and f of a squared is f of a times f of a. So this is in fact f of a the whole cube, and I'm representing the whole cube as product taken thrice, that's it. So f of a here is a square, so it is a square, and that is raised to a power of 3. So that means a power 2 times 3. So here I will represent it as 2 times 2. And now if you list down any random a part t, that will be f of a whole part t as it respects the group operation. Now this would be a square whole part t, and that is a part 2 times t. So now we want this to be a group automorphism, implying that it is injective and surjective. So already the element E is mapped to the identity element in the group, which means no other element can map to E other than E. Therefore, we must have a square, a part 2 times 2, a part 2 times 3, a part 2 times 4, and so on up to a part 2 times n minus 1. All of these not to be equal to the identity. That is the requirement. This implies that none of the exponents are divisible by n. It must be not divisible by n. The exponents in this enumeration should not be a multiple of n, and therefore we must have this power to be co-prime to n. That is the condition. So the GCD of 2 comma n must be 1. If it were not 1, I can multiply some number less than n minus 1 to have it a multiple of n. Hence, here the automorphisms are thus formed by mapping A to exponents of A or powers of A, where the exponent value is co-prime to n, and hence the total number of possible such automorphisms would be the number of numbers co-prime to n and less than n, which is exactly phi of n. So therefore, I will have the function, let's take an example to understand this. Suppose you have E, A squared and A cube. E, A squared and A cube. So this has order 4, and for this E must map to E to be an automorphism. A can only map to A or A cube. There are 2 possible functions then. The reason is that A square, the exponent of A square, 2, is not co-prime with 4. That's why. The 2 possible functions are just identity and another function f, where f is defined to be f of a equal a cube. The identity will have f of a equals a. So there are only 2 functions, and it turns out here that the automorphism G, where G is like cyclic group of order 4, is cyclic. But let's go in general now. For it to be cyclic, it must be generated by exactly one element. So if you have f as one function, one automorphism, then all the other automorphisms are generated by this function f. So say up to some f bar k. And it turns out that there are no function which is a group automorphism and not a power of this function f. This means that I can obtain the functional value g of a to be any co-prime power of a where the exponent is co-prime to n. So let's take the exponent to be r. GCD of r comma n equal 1, and this can be represented as some power of the function f. power here means that repeated composition. So if I assume f of a equal a power t with some GCD of t comma n equal 1, then think about the function f squared of a. This means f of a power t, which will be a power t square. Then consider f power 3 of a, that will be f of f power 2 of a, which is f of a power t square, and that will be a power t cube, and so on. So by this, I can only map the value a to a power of a with powers as powers of t, like t power 1, a power t power 2, and so on, up to some a power t power l. This should generate all the coprime powers of a to n, coprime to n, I mean, like this. It should generate all possible g of a. But this is only possible if you have a primitive root modulo n. So this is possible if and only if t is a primitive root modulo n. Because only primitive roots, when raised to higher powers, can generate all the coprime numbers less than n. But what if the number n does not have a primitive root modulo itself? For example, the numbers that have primitive roots only include 2 for some p power of a odd prime, or 2 into power of an odd prime. P is an odd prime. Please comment us your ideas in the comment box. We will get back to you soon. Thank you everyone. Bye.